let's start. So my lecture will be on hashing. So it's sort of everything about hashing that you wanted to ask but didn't ask. So here I put a quote from Udi Manber. So Udi Manber is a theoretician originally who worked in different companies, Facebook, I think, and Yahoo at this time. And he said that when he worked in Yahoo, so he said that the most important technique behind Yahoo are hashing, hashing, and hashing. So hashing is absolutely fundamental in both practice and also theoretical research. So now I want to also to poll you a little bit and to ask what is your background. So I mean, I know that you had some course in algorithms, of course, and probably you know something about hashing. So my question is, do you know hash tables? So I think you know hash tables. Everyone knows hash. Do you know hash tables? Say yes or no on Zoom.
No.
Yes. Do you know perfect hashing? Идеальное хеширование? No, okay. Okay, no problem. I just want to know if you... Do you know Bloom filters? Фильтры Блума? No, it's just for me to know how fast should I go on certain topics. So, okay, so no answer, right? Or, okay, okay, so let's start. And I will try to adjust to the situation and to... if I feel that it's too easy for you, then I will speed up and on some parts. Okay, let's do this. So so let's get started. So I want to spend the first 10 minutes maybe on kind of summary on hash tables, just to set up the scene, you know. So so what is going on? It worked. My pointer worked, but now it doesn't. Okay. Okay. So what are hash tables? So everybody knows what are hash tables. So hash tables are data structure for storing objects. So they are sort of containers. And so what they are capable of doing, so it's to maintain a possibly evolving set of objects that belong to a very large universe. So hash tables support so-called associative arrays. So it means that objects are specified by some keys. So sometimes keys are objects themselves. Sometimes keys are just identifiers of objects. And therefore, to address the object, we address it through its key. So hash tables have numerous applications. So they can play the role of index. They serve to so they are data containers, already said. So they are often used for deduplication. It means that when we have, for example, a stream of objects, we need to know if you have seen this object before. We look it up in a hash table, and this is a way to know if we saw it before or not. And in many other applications. So a bit of notation. So we have a huge universe of keys. This can be IP addresses, strings, names, ID, numbers, social security numbers, such kind of things. The number of possible keys is very big. So we have an actual set of keys, which is much smaller than the universe. So we denote by n the size of it, but knowing that n is not a fixed number because the set is evolving, so it's sort of estimate of the cardinality of this set. So hash tables support these three basic operations: inserting an object, deleting an object, and looking up for an object, which means look up means that we find out if the object is in our set, and if yes, we can access the object. So these three operations are as seen as an abstract data type, are usually called dictionary. Okay, so the key ingredient of hash tables are, of course, hash functions. And hash functions so provides a way to access the object. So hash function tells us where the object in which bucket of the hash table, which is simply an array. So in which entry of this array our object is stored. So the value of the hash function is usually called the hash value or simply hash. So hash tables is a sort of indirect addressing of our objects, in contrast to simple arrays where address objects directly. So the main problem, let's say, of hash tables is collisions. So collisions means that several objects can map to the same entry of the hash table, and this is of course unavoidable because we have a huge universe and a small hash table. So by pigeonhole principle, there is always possible that there are many objects that map to the same bucket of the hash table. So how to deal with collisions? Well, first of all, to illustrate the phenomenon of collisions, there is this famous birthday paradox, which is not a paradox, which you probably know, that asks what is the probability that two people from a group have the same birthday. So it's a kind of hashing, right? We hash people to their birthdays. There are 365 possible birthdays, right? And what is the probability of a collision? So I think you know this paradox, so-called. It's not a paradox that I put quotes because it just means that we are not very well in estimating probabilities actually. So you know that the probability is very high, and even if you have a group of 23 people already, the chances that two of them have the same birthday is already about 50%. So this illustrates that collisions are very common, very frequent, and we need to deal with them. So how do we deal with them? There are two main approaches, two main methods to deal with collisions. One is called chaining, and the chaining is very simple. So rather than storing, if we have several objects mapped, hashed to the same bucket, then we store a list. We store a list at this bucket with holding these objects. Okay, so several objects mapping to the bucket, we have a list. So this method, what is the let's say the complexity of this method? How much the operations would cost with this method? So inserting is very easy because we insert an object, we just append it to the head of the list. So it's a constant time operation. Look up and delete take time which is proportional to the length of the list, right? And if we assume that all objects, if we assume that each object has the same probability of being mapped to each bucket, so-called uniform hashing hypothesis, then the lookup and deletion take time 1 plus alpha, where alpha is the number of objects per average number of objects per bucket. So number of objects divided by the size of the tables, which is called load factor. We will come back to this later. So typically alpha is some constant. So we have usually the size of the hash table is proportional to the number of objects. So alpha can be 2, 3, or something like this, some small constant. So we have a constant time operation, a constant time lookup and delete in the expectation under this assumption. So you understand from this that a good hash function should distribute objects as uniformly as possible to make these lists as small as possible on average. It's not how to say, it's not so easy to define a good hash function. There are several standard methods. So a good hash function should distribute, as I just said, objects, try to distribute objects uniformly, and also it should be very efficiently computable. So the computing hash function should be very easy. So typically it's just some small number of operations. So there are some standard methods of designing hash functions, division method, multiplication method. I don't want to go into them. I think you probably know them, or if not, you can read any algorithm book and find them. These are very easy and intuitive things, even if there are some mathematical analysis behind it, which can also be interesting. But I don't want to focus on this today. So it's a pretty standard things, and you can find it in an algorithm book. So the second method for dealing with collisions is the so-called open addressing. In open addressing, we don't have lists. We allocate sufficiently large memory to store all objects in the hash table. So here the load factor should be smaller than 1. So we should have more buckets than we should have more buckets than the objects that we store in the table. So here the hash function has sort of two arguments. What does this mean? So this means that we go to the primary bucket for the object. If it's occupied by another object, then they move to the second option, let's say, then to the third, fourth, until we find an empty bucket where we place the object. So we should define a sequence of so-called probes. So this means that when we insert a key k, so we first go to bucket hk0. If it's occupied, we go to the bucket hk1, hk2, etc., until we find an empty bucket. So we have this sequence of probes, and so we have this sequence. So ideally, this sequence is a permutation. In the ideal situation, we should go through all somehow through all buckets in the table. This would be good. So the one problem with this scheme is that deletions become complicated, because we cannot simply delete an object, because we sort of interrupt this chain, and when we look up for another object later, it might be that we will not find it, right? So this is a problem with open addressing. So deletions are not easily supported. So the complexity of so there are again several standard ways of defining this sequences of probes. There is so-called linear probe, which is very simple. It says if the bucket is occupied, go to the next one. So it's a very simple strategy, but not very good in practice. So there is quadratic probing, where this function h is defined by by quadratic function on J on the iteration. And there is a double hashing where we have two hash functions, one hash function for the primary location, for the primary bucket, and the second hash function for the shift. So the shift is defined by another hash function. So these are again some standard ways of implementing open addressing.
Okay.
Yes.
You say when open addressing is better than chaining, when people like open addressing more than chaining?
Why or when?
Yeah, application situations.
Open addressing is more space efficient. We don't have pointers, we don't have lists. So this is the main reason why open addressing is advantageous.
Space efficient is just a small constant factor.
No, everything here is linear. Yeah, so it's constant factor. Yeah, but implementing lists is usually costly in practice. So
slower.
Yeah, slower, costly. Yeah, because pointers need to be stored also, and yeah, this takes space. Okay, so performance of open addressing, it can be proved very easily. Again, I think I will skip the proof because it's not a main focus today. So the complexity of insertion in your object or unsuccessful search, which takes the same time, is given by this formula, which comes from a geometric progression, which it's not so complicated. It's a simple probabilistic reasoning, and you can actually see this. And successful search is its complexity is also has been analyzed. Is given by this formula. This you can find again in Corman's book and other books. Okay, so this is just a reminder of hash tables. So we have this chaining, open addressing. So chaining is maybe easy to implement and also faster maybe, but takes more memory. Open addressing is more memory efficient. And of course, there are many implementations. In all programming languages, we have standard implementations of hash tables, and this is all over the place. So now, okay, so after this quick introduction or reminder, I want to talk about, in my view, more interesting things, and maybe a little bit more advanced. So the first thing I want to talk about is so-called universal hashing. And I think you don't know it. If you know it, if you know universal hashing, please raise a hand in the chat. I just would be curious to know if.
Come on, John.
Okay. No, it's not to test you. It's just to know if you know this or not. Universal hashing. What is this? So universal hashing is about collisions. So I mentioned in the beginning that we cannot avoid collisions.
If I'm not mistaken, it was mentioned in Corman book.
Yes, it is in Corman book with an asterisk, I think. Yes, it's in Corman book. Yes. Maybe without. I think it's with an asterisk. It is in Corman book. Yes. But what I'm going to show is not exactly from Corman's book. So what is this about? So this is about collisions. So we cannot avoid collisions in the worst case. So this is not possible because we have a huge universe, we have a small table, and it's always possible that all the objects that we receive go to the same bucket. So this is always possible. So and this is a problem. So the problem. Imagine that there is some malicious adversary who wants to break your program, to break your system, and it somehow gets the the code of your hash function, for example, if your code is open, he can just see it in the code, or if your code is not available, he can maybe reverse engineer your hash function. And what he can do, if he wants to harm your program, so he can supply to your program these objects that all go to the same bucket, and this will blow up your implementation. So this is actually, so this can represent a sort of attack. This is actually a real problem. So here I copied a page from a scientific paper from 2003, which is precisely about this. So they say that, if you read what is underlined here, so they say that yes, we can avoid this by using binary trees or other containers, but this is not efficient. If we want to use hash table, we always have this danger that such kind of attack would occur. I think I have another more practical example. So here, this is a web page that I found about breaking a murmur hash function. So murmur hash function is a popular practical implementation of a hash function, and on this web page, the authors describe a way of an attack to actually breaking here means precisely this. It means precisely being able to provide items which all go to the, most of them maybe go to the same bucket. So it's not a completely artificial problem. It's a real problem. So now I want to introduce an important concept which can be seen as a way to deal with this danger, with this kind of attacks. So the idea is to use randomness. So so the idea is to use not a specific hash function, not a single hash function, but a family of hash functions, and we will pick a specific hash function randomly from this family. And we will do this at the execution time. So this means that the adversary will have no means to know in advance which hash function will be chosen, so he has no possibility to prepare his data set to break our implementation. So that's a nice idea. So in many, randomness is used in many situations in computer science, and also plays different roles. But here is an example where randomness is used for sort of security reasons. So I think it's a nice idea. So what we want to define is a family of hash functions. Such a family will be called universal if it verifies the following definition. So for any pair of keys, KL, fixed pair of keys, the probability that they collide, that they hash to the same bucket, is at most 1 over m, where m is the size of the hash table. So what is important in this definition is that the probability is taken over the hash functions and not over some distribution on data.
And k should differ from L.
Yes, k different from L. Sorry, yeah, I should have maybe specified it. So so the probability is taken on the hash function. So if you pick a random hash function, then the probability that they hash to the same bucket is 1 over m at most. So an equivalent way of saying this is to say that the fraction of hash functions in H which map K and L to the same bucket is no more than 1 over m fraction of all functions. So this definition is looks like easy, but maybe you need a moment to digest it.
Yeah. Any pair, you mean for every pair?
Yes, every so.
Any is dangerous word because it can mean there exists a pair or.
No. K and L are. K and L is a fixed but arbitrary pair of keys.
Yeah.
Okay.
For all pairs of different keys.
You can say for all, yes, but yeah, but you can say for all, for any, I would say.
Well,
yeah.
Any is dangerous, word because it means has anyone.
Okay, I understand. No, not there exists. But for any instance, for every, okay, for every.
Yeah, for every.
Okay. Okay, so this looks like this uniform hashing hypothesis that I mentioned at the beginning, but it's very different because here we have a probabilistic space which is H here. So the probability is taken, and this is maybe the guiding idea of also other hashing applications that I will show later, because it's a very good idea actually not to define a single fixed hash function, but to have a family of hash functions and to pick a hash function randomly from it. Because we often need not one hash function but several hash functions, and it's a good to parameterize the hash functions and to have a family of hash functions. So if we have this family of universal, so if we have a universal family, then the expected time of operations, insertions, deletion, and lookup become 1 plus alpha basically. Well, yeah. So it becomes proportional to the load factor. So again, here the expected time, you should understand that the expected time means, again, with respect to the choice of the hash function. So we so there is no assumption on the distribution of keys here.
And so when there is collision, you do chaining or?
Yeah, this is with chaining. Yeah.
Oh, sorry.
Yeah. It's actually it's with chaining, but it's not so important here because it's not about how to store. It's about it's about Okay, let's say that it's with chaining. Yeah. So this is easy to prove. It's almost immediate. It's just an immediate consequence of the definition. No questions? Fine. Okay. So how to construct universal family of hash functions, and do they ever exist? So this is not immediate from the definition. So there are several. I don't know how many, but there are. I know about several different ways of defining universal families. So one is given in Corman, but here I give this is the simplest definition of universal family of hash functions that I know, and it's much simpler than the definition than the construction from Corman.
But just a set of all functions is.
No, it's no, the set of
So then picking 2 elements, 2 keys will have
no, let's come back to this discussion later. So it's I'll answer this later. So so here is a way of here is a definition. Here is a construction of universal family. So we assume keys are u-bit numbers, okay, and the size of the hash table is 2 to some w. So the hash values are w-bit numbers. Okay, so hash table maps a u-bit number to w-bit number. So w, of course, is smaller than u. So so we will parameterize. So our hash function will be basically a random w by u Boolean matrix, 0, 1 matrix. Okay, and this will be our hash function. So the application of a hash function h m, so h function defined by matrix m to a key k will be will be this matrix m multiplied by k, where the multiplication is done over XOR and AND. Okay, so instead of the usual Boolean multiplication is OR AND, but here we do XOR AND. Okay. So you know how matrices how we multiply matrix by vector in a Boolean ring, right? Usually this is OR AND, but here it's XOR AND. So for example, if you multiply this matrix by this vector, this will be 1, 1, 0. Whereas in the usual Boolean matrix multiplication, this would be 1, 1, 1, right? Because here we have so basically the multiplication here means that we are XORing columns corresponding to ones in the vector, right? So in this example, we are XORing first and the third columns. And now I claim that this is a universal family. So it means that if I pick two keys, k and l, distinct keys, then the probability that they collide will be no more than 1 over 2 to the w, so 1 over m. So how do you prove this? So since k and l are distinct, there is at least one bit where they differ, right? And assume that k has 0 in this bit and l has 1, for example. Okay? So now maybe I should draw something. So have our matrix. We have x, k. So k has 0 at this place, I. And the result will not depend on the i's column, right? The result of this is h of k. So the result will not depend on the i's column, right? Because i's bit in k is 0, so the i's column in our hash functions, let's say, doesn't affect the result. So now we multiply the same matrix by L, and L has 1 at this position, right? So the result will depend, of course, on the i's column, and moreover, for different columns, we'll have different results, because this is XOR. Okay, by XORing with different vectors by different vectors of size m, by size w, we will have different results. Okay? This is the key point of the proof. This is because of the properties of XOR operation. Okay? And clear this? And therefore, the probability that they will collide is obviously 1 over all possible vectors, which is 2 to the W.
So only if you have a column with all zeros, then there will be a collation.
Yeah, provided that all the other bits are the same.
Yeah, in the worst case, only one bit differs.
Okay? Clear? Okay. So this is the simplest construction of the universal family that I know. But there are others. If there are questions in the chat or maybe, okay. So feel free to ask questions if you have any. Okay, then I continue. I assume that this is fine. Okay, so there are other constructions. So here I give another one, which is also not from Corbin's book, but similar to the one from Corbin's book. And here the construction is the following. So here we use properties of prime numbers. We use modular arithmetic here, which is widely used in this hashing business. So here I assume that our keys are tuples of numbers. And this is also a very common situation. For example, when we hash strings of fixed lengths, they are also tuples, right? Or it's quite common that keys can be represented as tuples of numbers. So here I give an example of IP addresses, but this can be extended to, this is just for the purpose of an example, but the construction is more general. So assume we are hashing IP addresses. So an IP address is a quadruple of numbers from between 0 and 2555. So what we do is the following. So we choose the size of the hash table to be a prime number larger than 255. Okay. So here we need a prime number. That's why I called it prime table size. So we need a prime number. And here our hash functions will be parameterized by a quadruple also of numbers between 0 and m-1 picked randomly. Okay. So so our hash function will be parameterized by 4 numbers. Okay. And the definition of the hash function is here. So it's a linear combination of a1 times x1, a2, x2, etc., modulo m. So it's claimed that this is a universal family. And the proof is actually sort of similar to the proof to this proof. Interestingly enough, it's pretty similar actually. So the proof goes like this. So assume we have two keys again, k and l, which are distinct. So keys for numbers, l is for numbers, and assume since they are different, they should differ in some corresponding pair of numbers. For example, case 3, I just picked for the purpose of example, for the purpose of the example. So assume that case 3 is different from L3. and then, so if they collide, then, well, if they collide, it means that this modulo m equals this, I mean, HA of k modulo e. I should maybe write it down. So it means that, okay, let me write it down. So assume they collide. So it means that A1 K1 plus A2 K2 plus A3 K3 plus A4 K4 equals the same for L, A1 L1 plus A2 L2 plus A3 L3 plus A4 L4 modulo M. Okay, then we can rewrite this as here. Okay, we can rewrite this in this way. And since K3 minus L3 is not 0, and also smaller than m, then we can, by the properties of model, and m is prime, we can actually take the inverse. And A3 is defined uniquely, actually, from this.
After fixing A1, A2, and A4,
yeah,
then we still have to pick A3 and only
yes,
one.
only one. Yes, only one value of S3 verifies this equality, which means that for these keys to collide, the probability is 1 over all possible choices of the number of choices for A3, which is 1 over m. So you see, it's a similar idea actually, but different. So this is another useful definition of universal families of hash functions. And I repeat that this is more general that I present here on this slide. This can be also applied to strings, for example, which is very common situation that we hash strings of fixed size. And this works in more general setting. Okay, I should follow the time. Yeah, we have. So this is a construction from Corbin that I will not explain. In my view, it's more complicated, but actually the idea of Corbin's construction is very similar to this one. But rather than working with tuples, we work with just numbers. And we have to pick a prime number which is very big, which is bigger than any key. And in practice, we well, this is a general construction. Okay, it works without any special assumptions, and it's in practice more efficient than the matrix construction that I showed at the beginning. This is similar to the previous one. We choose a big prime number. So in practice, we choose, for example, 2 to the 31 minus 1. If we are working with 32-bit numbers, this is a prime number. And 2 to the 61 minus 1, if we work on 64-bit architecture, this is also a prime number. These are so-called Mersenne primes. So this can be chosen, and then the definition of the hash function is here. So it depends on two parameters, a and b, both between 0 and
but p has to be larger than m.
Yeah.
If m is 64
No, p
bits,
not only larger than m, but it can be it should be larger than any the key value. That,
okay,
yeah, it's a very big.
But then the last line of the slide, the maximal key value for 64-bit numbers is 2 to the 64.
Yeah, but okay, yeah, but we assume that that keys are I don't know, maybe 60-bit is enough to store a key or something like this. Yeah. Okay, I will not explain the proof. It's again it's a bit similar to the previous one, but maybe a little bit more involved, and I don't want to explain it. Okay. So again, I refer you to Corman's book for this proof. So one more. One more remark on universal families, universal hashing. Actually, the research continues, and some new methods some new constructions of universal families are still being proposed in the literature. So you see this paper, for example, is very recent, just 2 years ago. And here is yet another construction which is actually very simple, and it seems to be I don't remember if it's really, strictly speaking, universal or maybe close to universal, but here the construction is simple. So what we do is we multiply our key x by a random number a. So a is a random number of w bits. So assume we are hashing, our keys take w bits. And we hash it to L bits. So we multiply it by a random number of W bits. So we obtain a number with 2 W bits. And then maybe it's better to write a. So we have a key X of W bits. We have a random number A of W bits. So we multiply them, we obtain a number of 2W bits, and then we take the less significant W bits, and then we take these L bits from it. And this will be our hash. So as simple as this. And it seems that this works very well. This is very easily implemented by bit shift operations. And it seems that in practice this works very well and represents a universal family. Okay, so I'm just telling you that this, how to say, this research continues, and you know, the very, very simple and efficient ways of defining hash function is still.
So the last paper, it's empirical or theoretical paper?
No, I think it's a theoretical paper. Yeah,
Okay.
but because Mikhail Torap is a well-known theoretician in.
Okay.
Okay, so I think this finishes my chapter on universal hashing. Ask me questions if you have any about universal hashing. I I remember your question. We will continue on this. Okay. No questions? No?
Questions so far?
Okay. Okay, now about the next topic is perfect hashing, is идеальное хеширование. I think in Russian it's like this. I don't know Russian terms, but this I know. So again, the same question as before. Do you know perfect hashing? Do you? Because I know that there is a in your program, I took a look at your program in advanced algorithm course, and I think perfect hashing is there. So no answer, no.
No answers yet.
No, I mean, if you heard about it but you don't remember, it's fine. I mean, I will.
It's with logarithmic smaller tables. Is this perfect?
No.
Then I also don't know.
Okay, let me now go to this perfect hashing. Perfect.
I have one answer. Know what it is. Didn't quite understand how to build it.
Say it again, please. Yeah.
Know what it is. Didn't quite understand how to build it.
Okay, so I'll try to explain. So good. So again, what is it about? First of all, so it's a different problematic. So here the question we ask is that can we ensure the worst case constant time for lookup? So we know that in classical hashing that I presented in the beginning, the lookup time is proportional to the load factor, which is so no, it's not. So we know that we know that
lookup time was of 1, you said.
Yeah, on average. But here I'm talking about worst case.
Yeah.
So we want to guarantee that in the worst case we spend a constant time. Well, of course, this is not possible, as I already said several times, because we can always have a situation when we are receiving objects that map to the same bucket. So we need more assumptions. We need some more assumptions here. And the assumption, one assumption that we can add to guarantee this is that the set of keys is static. It means that the set of keys that we have to store in our table is given once for all in advance, and we can, for example, go through it several times. So it's not something that we dynamically receive from a stream, for example, or things like this. So we have a static set of keys, and we want to construct a hash table where we, given a key, we look it up in constant time. So this is actually not. It also sort of requires some thinking, because often we are. I think I have next. So one solution is very easy. So we can sort our set of keys. So after sorting it, each key will have a rank. Each key will have a rank in this list, and if a key has rank I, so we will store it in the i's bucket.
But then evaluation of the hash. What is the hash function?
Yes, evaluation of the hash will be find the rank and go to the corresponding, find the rank of a key. Yes, it's a good question, because the evaluation will no more be constant. So we will need, for example, to do binary search over this list to find the rank of the query key. So okay, I repeat. So in practice, it's quite common that we already have our set sorted. For example, if it's given in some order, and if it's given in an array, I don't know how. It depends on the representation of your input of the set. But even if it's sorted already, then still the computation of the hash function will be logarithmic, because you need to do some binary search. So here the question is, can we store a set in a linear space so that we have still a lookup function working in worst case constant time? This is basically.
And when you say constant time, you
worst case. Worst case.
That the load is smaller than 1, alpha is smaller than 1, or you.
Yes. Alpha is smaller than 1 here. Yeah.
And you allow some operation to run in constant time because you need to evaluate some.
Yes. We assume that evaluation of a hash function, it takes constant time. Yeah, we assume that evaluating a hash function takes a constant time. Yes.
So you.
For example, universal family of hash function that I just presented before.
Okay.
So the evaluation takes constant time.
Yes,
so
the comparison of keys is also constant time, or.
Comparison of keys is constant time. Yes. Yes. Is the problem clear? Because the problem here is not so immediate, actually. It's a problem that has been that was known under the name something like should data be sorted or should tables be sorted. It was actually an open question for some time. If we can do this, if we can store a set in a linear space and look up to support lookup in worst case constant time. No questions in the chat? No?
No.
If you have questions, please ask. So I need some interaction because it's difficult to to talk to the camera. Okay, so I continue then if there is no question, because this is not so easy to grasp maybe the problem. Okay, so the solution that I will present is a solution where so the price that we pay, well, one price I already mentioned, that the set is static, but the other price, or the construction that I will present in a moment, is that the construction time of the hash table will take an expected linear time. So the construction will be non-deterministic, and because it will use a random choice of hash functions, so like in the universal hashing, and therefore the time of the algorithm will be non-deterministic, and it will only take take linear time, but only in expectation. So it's called Las Vegas algorithm. I don't know if you know this. If you know, no. Okay. Let me say a word about probabilistic algorithms in general. So probabilistic algorithms are algorithms which use probability, which flip a coin, if you want, which take some steps randomly, and there are two different situations. So one situation is when the algorithm is always give the answer, the correct answer, but its execution time is guaranteed only in expectation. Okay, so this is one situation when the algorithm returns the answer, the correct answer, but the time it takes is probabilistic, and there is a very small maybe probability that the algorithm will take a lot of time to give the answer. But maybe on average, on expectation, it will be fast, but with very small probability it can be, for example, the number of iterations it should make can be with very small probability it can be large, for example. So this type of algorithm is called Las Vegas algorithm. And the other type of probabilistic algorithm is when the answer may not be exact or may not be correct. With very small probability, the algorithm can make mistake. So this is another type of probabilistic algorithms which is called Monte Carlo algorithms. So this is a Las Vegas type algorithm. So it will always construct a desired data structure, but the time will be only in expectation. So let's go to the construction. But before going to the construction, we need a little reminder from this birthday paradox. So let's first estimate what is the expected number of collisions. What is the expected number of collisions? So what is the number of pairs of distinct keys which hash to the same bucket if we have this uniform hash hypothesis? So this is not so difficult to estimate. So let's introduce an indicator random variable xkl equals 1 if they hash to the same bucket. So the expectation of the number of collisions is the expectation of the sum of these indicator variables for k different from L. So by linearity of expectation, this is of course the sum of expectations, and this will the expectation of this random variable is 1 over m by our hypothesis, and this n choose 2 different pairs. So we have roughly n squared over 2m collisions. So this is a good thing to remember, because you see that if size of the table m is quadratic with respect to the number of objects, then we have a constant expectation. So the number of collisions will be constant. So if you so if, for example, if the size of the table is n squared, then we have 1/2 expected collisions. Okay. And by Markov inequality, which I recall here in this frame, so we have the probability of having any collision is less than 1/2. And this explains the birthday paradox, because in birthday paradox we have n equals m equals 365, right, the number of days, and n is the number of people. If n is roughly square root of m, something like this, and 23 is very roughly square root of 365. Well, actually the square root of 365 is less than 23, but roughly the same order. No, it's not factor 2. It's because of this border. It's just an estimate. It's not. There are some border conditions. Let's say border effect. So so this is good thing to know, that if the the size of the hash table is quadratic with respect to the number of objects stored, then the collisions will basically disappear. So assume we have this situation. Assume we have very few objects with respect to the size of the hash table. Assume we have this situation, and we want to construct a table without collisions. How we can do? But we can proceed by trial and error. This is the most stupid approach that we can think about. So we just pick a random hash function, construct a hash table. If there are collisions, we start again. We pick another one, and we start we construct a hash table until we obtain a hash table without collisions. And this is how often probabilistic algorithms work. Because if we have a constant probability of something bad, then we can always, by iterating, get rid of this. So in a constant number of rounds in expectation. So since the probability of having collision will decrease exponentially with the number of trials, with the number of rounds, then in a constant number of rounds in expectation, we will reach a desired situation where we have no collisions. Okay? And this we will use. So so this is now the construction that was proposed in this work long ago, in '84. These are very famous mathematicians, by the way. Semiredi is I don't remember which, maybe Abel Prize or some very. So these are very famous combinatorists. So they are mathematicians, but they did this work in computer science as a by result, I think, as a byproduct of. So we have a static set of keys, and we want to construct a hash table where we have actually a constant number of keys in a bucket, but in this construction we will even have only one key in a bucket. So the idea is that to introduce a two-level hash scheme. So we will have a normal hash table, usual hash table, the first level, and then for those buckets which receive several keys, we will construct another hash table. So we will then store them in another hash table. And the size of this second level hash table will be quadratic with respect to the number of items hashed to this bucket. Okay? So I repeat. So we hash, we pick a hash function. We hash our keys to a hash table in the usual way, and then for those buckets which received several keys, we construct another hash table, and the size of this another hash table is quadratic with respect to the number of keys hashed to this bucket. No question in the chat?
Let me check. No.
Okay. So if we succeed to do this, then the worst case lookup will be obviously constant. So we just go to the corresponding bucket. If if it is an ambiguous bucket, then we go to the second hash table and pick the the object. So the whole point is how to, well, there are two questions here. So one question is why this is linear space. So these are quadratic size hash tables, and it's not obvious, and all this thing takes a linear, well, this is obviously linear space because the size of the hash table is a constant factor away from the number of objects, but it's not obvious that these second level hash tables will take a linear space. This is the first point, and the second point is how we construct this. I mean, so the first question is why this is linear space. More precisely, why this can be made linear space. Because it can happen that, for example, as an extreme situation, it can happen that all the objects map to the same bucket. In this case, it will not be linear space, obviously, because this is a quadratic number, quadratic size, how to say. Yeah, this is takes a quadratic space with respect to the number of objects. So in the worst case, it may be a quadratic space, but we can make it linear space by several trials, let's say. So what is the expected size? What is the expected total size of this second level hash tables? So the expected total size is this sum of squares of ni's, right? So and this is if we think about it a little bit, so this is actually the number of pairs which collide, because what is ni square? So ni square can be reformulated, how to say, can be expressed as the number of pairs in this set. Okay, do you follow me? So we have ni objects. We have a set with we have a set S with ni objects. Okay. What is the ni square? So ni square is the number of pairs. Okay, ni square, if ni is the cardinality of the set, ni square is the number of pairs of this set. So it's just and the number of pairs we already know how to estimate. So a number of pairs is this expected number of collisions. Okay? Total number of collisions. Okay? This will be. So now if we compute this, n plus, so we substitute here, what we substitute? We substitute.
M equals to n?
Yes. Yeah, we substitute, yes. So number of, yeah, so
yeah, so you should divide by m and you set n equal to 2n.
Yeah.
So the denominator is a typo.
So here I assume that the size of the hash table is 2n, right?
Yeah.
And
you should have written m in the denominator.
Yes, but I don't see where I said that it's 2n. I should say it somewhere. Maybe I.
Top line of the slide you said.
No, but this is no. We should set the size of the hash table, but I don't remember if maybe n or 2n. But anyway, it's some constant times n. So the expected number of pairs, which collide is n here. okay, which shows that the sum of the expectation of the sum of squares, sorry, the expectation of the sum of sizes of these second level hash tables is 2n. It's written here. So we are approaching the break, I think. What time is it? Yeah, it's time for break. So should we just
finish and then 5 minutes or something?
20.
Huh?
20 minutes.
No, okay, but can I take a few more minutes to finish? Okay. And yeah, I'll take another 5 minutes and then we make a break. So, the expectation of the total size of the second level hash tables is 2n. Okay? And by Markov inequality, the probability that it's more than, say, 4n is less than 1/2. And this is again the same idea. So we can, by trial and error, we can make several trials, and in a constant number of rounds and expectation, we will reach the situation when the total sum of these second level hash tables will be small enough, will be linear. Okay? So here is the algorithm, which if you have never seen probabilistic algorithm, this will look strange to you, but this is quite typical for probabilistic algorithm. So this is how the algorithm works. So we hash to the primary table of some linear size, 2n maybe, using universal hash function. We hash each, say, non-empty bucket, say, to a table of size ni square. So if we obtained the total sum of the second level hash tables more than 4n, then we rehash. And that's it. So yeah, and so here when we don't even construct yet the second level hash tables. We just count the number of objects that collided to the same bucket. Okay, so even before constructing the second level hash table, we can also so basically what we do here in the first two steps, we want to make several trials until we reach a situation where the objects are distributed uniformly enough. Okay, and once they are distributed uniformly enough, we construct the second level hash tables, and here again we may need several trials, and overall, in a constant number of trials and expectation, we will reach the desired situation. Break. Okay, so let me conclude with perfect hashing. So I presented this construction. So one thing to mention is that this is actually practical, so you shouldn't think that this is purely theoretical construction. Actually, perfect hashing is something which is used in practice, and there are some implementations of perfect hashing. So let me summarize again what we did to make it clear. So we now have a constant time lookup. So we now can look up for an object and access an object in worst case constant time. But we have some price, right? The price is first that the set is static. So this is one price that we paid for it. And the second price is that the construction time was expected, right? So the space, we construct a linear space hash table, but the construction time with very small probability can be long, because we can make many trials, many iterations before we reach the desired, before we construct the desired structure. So to conclude with this topic of perfect hashing, I want to mention another thing which I just mentioned. I will not go into it, I will not explain it. I just mentioned that this exists, which is called minimal perfect hashing. So minimal means that not only we have a hash table of linear size with respect to the number of objects, but we have a hash table which with exactly n buckets. So the size of hash table is equal to the number of objects. So basically, what this means? This means that we enumerate our objects from 1 to n and store them in an array of size n. Okay, so it's basically a sort of enumeration of keys. But this construction is more complex. So this requires more work and more effort, and this is something which is still ongoing. There is still ongoing research. You see that there are papers are pretty recent here, and another very important thing here is that the hash function which performs which supports this data structure. So the hash function that we construct here is not so simple. So the hash function itself takes space to store it. So it's the hash function itself here is a data structure. So and this data structure, moreover, has a lower bound with about 144 bits per key. So we need at least 144 bits per key to store this hash function. So this is a much more complex construction that we had before, but I just want to mention this to tell you that this exists also, minimal perfect hashing. So I just for you I just said that we can not only require that the size of the hash table is linear, but we can also require that the size of this hash table is exactly n. So we have precisely as many buckets as the object. So this is very strong, but the hash function that supports this construction is much more complex and requires space to store it. So this is a more complex situation. But the research is still ongoing here. Okay, so now my last topic about hash tables is Cuckoo Hashing. And Cuckoo Hashing is also sort of perfect hashing. Yes, so I could ask the same question to the audience, whether you know Cuckoo Hashing, because it's also something that is in the program of some algorithm courses. So could you raise the hand if you know Cuckoo Hashing, just to okay, it's just I don't see any hands.
Never heard about it.
Okay, so good. So I just want to make sure that it's not something that you all know. Okay, Cuckoo Hashing. So this is a very elegant and very nice hashing scheme, which can be also seen as a perfect hashing because lookup will be worst case constant time. But there is also some price to pay. So I'll tell you in a minute what is this price, but there is no miracle, of course. There is some price. So Cuckoo Hashing exploits the idea of choice. So this is a slide that I put, which is not in direct relation to Cuckoo Hashing, but it's just an illustration of the power of choice. So so assume we have n keys and buckets, and we distribute keys randomly to the buckets, and so the question, what is the fullest bucket? What the fullest bucket will be? So the probability theory, there is some analysis that tells us that the fullest bucket will be of size log n, or more precisely log n over log n. Okay, so again, we have n keys. We distribute them randomly to n buckets. Okay, so since we distribute randomly, some buckets will be empty, some buckets will receive several keys. So the question is, what will be the fullest keys? The fullest bucket. What will be the bucket with the maximum number of keys? So there is a probability theory tells us that they will be logarithmic. Okay, but now let us slightly change the scheme, and rather than using one hash function, we will use two hash functions, and we place a key. Before placing the key, we go to the two locations, and we see which is the less full, and place the bucket to the one which is less full. Okay, so each key we map it to two random buckets, and we place it to the one which is less full. Okay, and in this case, the fullest bucket will have log n keys. So the difference is enormous, right? The difference is exponential between log n and log n. So we basically have a huge gain here by having a choice between two buckets.
I don't understand.
You don't understand.
So for one bucket, you have log n?
The fullest one, the one with the maximum number of keys will have log n items.
And now every bucket is split into two?
No, not every bucket. We have this, still we have n buckets. And, but we have two hash functions. We have two,
Okay, yeah.
so to place a key, we not only we place it randomly to one bucket, but we place it. We choose randomly two buckets, and choose the one which is less full.
Okay, and so now it's dynamic setting.
Yes, this is dynamic setting. Yes.
And no deletions, I guess.
No, it's not. It's not a hashing. Yeah, it's just an illustration to the power of choice. What I'm showing here is that when we have a choice of two, because in the Cuckoo hashing we will use two hash functions. So when we have two options, then we have a huge gain. So this is an interesting mathematical illustration to the power of choice. You can push it philosophically further, and say that having a choice provides you a lot of gain in performance. So it's important to have a choice. Well, I will not speculate too much, but
but it's not working
what?
For every pair of two hash functions. So for example, if you hash two
no, here, I don't specify hash functions. If you want, you can even forget hash functions. Just randomly pick buckets. Or you can take a good hash function, like from a universal family, for example. It's not about hashing. It's about coupon collecting. It's about it's just a parenthesis. It's okay. Maybe I confused you more than. Okay, if you don't, never mind. It was just a digression, if you prefer. Okay, it's just a digression. It's not very important for what follows, but I just want to say that if we have two instead of one, then it will help. That's the message here. Okay, so in Cuckoo hashing, now we are back to hash tables. Okay, so we have a hash table as before, So this will be open addressing. So we will store everything in the hash table. Okay. So this will be open addressing. And so the big difference with respect to the previous setting is that here we will have two hash functions, h1 and h2, two independent hash functions. And we will guarantee that each item, each key, x, will be either in location h1 of x or in location h2 of x. In one of those locations. This will be invariant. This will be guaranteed by the scheme, by the algorithm. Okay? So if x is in our set, then we are sure that x is either in h1 of x or in h2 of x. So this immediately implies that lookup is constant time. We just have to go to both locations and check if the key is there or not. Very simple. And also deletion is supported. So we can also delete, because we will be able, if a key is there, we can just delete it without any harm. So it will not make any problem to delete. So what is a problem is to insert, because it may happen that we want to insert a key and both locations are occupied. So what we do? And what we do is that what Cuckoo bird does with its eggs, right? So it kicks out the egg of another bird and places its egg to the nest. So this is why it's called Cuckoo Hashing, because the principle is the same. So if we want to place a key to a bucket which is occupied, so what we do is that we kick out the key which is there and place our key there and place the key that was there, L, in the alternative bucket. Okay?
But then this alternative bucket
can be also occupied. Right. So we have an iterative process. So this is the algorithm for insertion, which will be iterative. So we try some of the two. Okay, let's look at this loop. So we are about to place a key x to a position pos. So if the position pos, if the location pos is empty, then we place the object there. If not, then we swap x with what is there, with the content of the bucket. So x becomes the new the key that was in this bucket, and then we look up for an alternative position of x, right? So the alternative position is easy to find, right? Because we have the two functions, so we know if this was the first or the second, right? This we can find out because we can just compare h1 of x and h2 of x with the current location and know if this was the first or the second. So we can find the alternative one. Okay? And we continue. So we iterate until we find an empty bucket.
And worst case time can be n.
Yes, worst case time can be n. And even worse, we can have a problem here, right?
H1 can be equal to H2?
Well, this can happen, but this is negligible. This is not important. This can also happen, yes, that H1 is equal to H2. In this case, we have a loop, sort of loop, right? So what is the problem here? So the problem is that we can loop, right? We can. It may happen that we run into a loop, right? We try to move one object to another place, and then the object that was there, we can try to move it back to the previous place, so we can run into some loop.
So, for example, if there are two objects x, for which both h1 and h2 are equal.
Yes, in this case, we definitely have a problem, yeah.
Sorry, not for 2, but for 3. If we have 3 objects, x1, x2,
Yeah,
x3.
for example, yeah. I think I have even an illustration. Okay, so this is an illustration to the process of insertion, but this I think you understood. So we assume we are inserting k, so assume that both locations are occupied. So we try h1, so we expel b and move b to the alternative location. Assume that the alternative location is, for example, here. Then we expel e and move it to alternative location, etc. Okay, so until so we expel d here, and maybe d maps here, and so we found the empty, so we place d. So this is how it works. And yes, we can have a loop. So we can have a loop like this, for example. So in this case, we would move b here, then e here, and then a back here, and then we run into a loop. That's what you said. Okay. So how we can deal with loops? So loops are easy to detect if we iterate sufficiently many times. So if we iterate if we have iterated 10 times and we are still not done, we have still not found an empty place, then we deal with a loop, right? So we have a loop. And when we have a loop, we just stupidly rehash. So we just start over. We rehash everything. So we take another hash functions and other hash functions, and we rehash everything. So the point is that loops are actually very rare if we allocated sufficient space. So this is the main point here. So the main thing about Cuckoo hashing is that if we allocated, say, twice more buckets that there are objects, or actually a little bit more, roughly twice, then loops will be very rare. Loops will be very rare on the one hand, and so rehashes will be rare also, and the amortized time of this rehashing amortized time of this rehashing will be very small. It will be actually constant per insertion, so even less than constant. And this is what I want to convince you about, that this is the only thing that we have to analyze here. Okay? So this is a sketch of the idea. So actually, interestingly enough, we are dealing with random graphs. So why? Because you see these locations in the hash table can be seen as nodes, and these arcs between two possible locations of each objects can be seen as edges in and a loop is a loop in this graph actually. Okay, I'm just reformulating this issue of loops. I'm just saying that it's very convenient to look at it as a loop in a graph.
So you will build the graph for each x that you want to insert, or for
so
the
each
whole strata structure?
So each object will correspond to an edge, and each location in the hash table will correspond to a node in the graph. So nodes in my graph will be locations, and edges will be objects, because each object covers two locations, right? So this is just a point of view, but I think it's a very convenient. If you adopt this viewpoint of graphs, then it will be easier to understand why loops are rare. And
what about this k element? Is it a part of a graph or not? The one that we hash.
Sorry, what about k element?
K, yeah.
K is a key. Yeah.
It's not within the structure of the graph.
No. I consider all keys. I consider all keys. So we have n keys, and I consider a graph over all keys. Yeah.
And so the graph, if there is an edge from A to B, there will also be from B to A.
Yeah, but I will consider non-oriented graph. So
okay,
yeah, I will consider non-oriented graph. So. So nodes are buckets and edges are inserted elements. Okay. So this is a random graph. Because we assume that hash functions are random, independent, and therefore all edges between pairs of nodes are equiprobable. So this is a random graph, right? We can model this at a random graph. No?
Oh, with unknown probability of
Sorry?
With unknown probability of distribution, right? A priori, it's not a model distribution behind. It's an empiric one.
No, here I'm in the simple assumption that everything is equiprobable. So the hash functions are good, so they distribute objects uniformly and also independent one from the other.
Sorry,
Yeah.
Every edge is basically a pair of buckets.
Yes, right.
Yeah. And so you assume that every pair of buckets is equally likely.
Yes, absolutely. Yes, I assume that every pair of buckets is equally likely. So what I'm saying now is that if we have few objects with respect to the size of, in other terms, if we have few edges compared to the number of nodes, then loops will be very, very, very unlikely, very rare in the graph. It's actually, for people who are familiar with random graphs, this is like a very basic facts. So, these are, if you know, for example, this Erdős-Renyi random graphs, then you know this phenomenon of phase transition, right? If we have n over 2, if we have number of edges is half the number of nodes, then we have a phase transition. And if we are below the phase transition, then the connected components will be very small, and actually loops will be very rare. So this is roughly what will happen in random graphs. So this is what happens here in cuckoo graphs. There is a term cuckoo graph. It's okay. So this is basically the intuition. So if we have less than m over 2 objects, so if the size of the hash table is a little bit more than twice more than the number of objects, then we will basically have no loops. And also the number of steps that we have to do before we find an empty bucket will be actually constant with high probability.
I don't understand how connected components is related to our problem.
Connected components are related because we, when we place an object, when we iterate through we basically stay inside the connected component of the graph, right?
Yeah.
So if we know that the connected components have constant size, then we are sure that the insertion will take constant time, right? So this is the intuition. If you understand this, you understand everything. So it's basically the explanation why Cuckoo Hashing works. Okay. So here I have a little theorem that actually the number of steps we have to do before we find an empty bucket decreases exponentially on some constant, let's say. So if we have, okay, to be more precise, if we have the number of objects which is less than m over 2 divided by something more than 1 plus delta, then the probability, then the shortest path from some node I to some node j is of length d will be less than 1 over m exponent of 1 plus delta. Okay, so it will decrease exponentially. So this is in terms of graphs. You can be so this means that if we have a random graph with few edges, then we start with subnode. So with probability less than, so the probability less than, I don't want to mix up notation because n is here the number of edges and m is the number of nodes, but usually it's the other way around. So it's easy to, so I will stay with this notation. So if the probability of an edge is less than m over 2, so if you start from some node and start to propagate, then it will be extinct very quickly. In a constant number of steps, the process will interrupt. So this says this is very easy to prove by induction. I think I put the proof here. It's a trivial proof by induction. So the basis of induction is what is the d equals 1, so it means that just one step. So what is the probability that we have an edge which connects I and j? So the probability the probability
1 divided by
yes, one divide. So we have no, it's not m choose 2, it's m square over 2 because we also allow, yeah. So we have m square over 2. So it's n divided by m square over 2, and since n is smaller than n over 2 divided by 1 plus delta, so we obtain this. Yeah, it's and the induction step is also easy. So we have a shortest path of length d plus 1, which means that we have a shortest path of length d to some intermediate node plus one node. So the probabilities multiply, and then we sum up over all intermediate nodes. So this, of course, we can have shortcuts. But shortcuts can only decrease the probability. They cannot increase. So they... okay, so this is just a quick proof that we have the probability that we reach another one node from another in d steps decreases exponentially with d. Okay, and therefore by summing up over all these, So the probability that some node is accessible from the other is 1 over m. Okay, so this is a sum over. And the number of accessible nodes is constant. So this is what happens when we have few nodes. Few edges, sorry, with respect to the number of nodes. Okay? So this is what, why cuckoo hashing works. And also there is some analysis about the rehashing, so how often are rehashing and what is amortized cost. I will skip the precise analysis, and I refer to these two texts, notes. So the first one is from Rasmus Pak, who is one of the inventors of cuckoo hashing, and he wrote a small note which is called Cuckoo Hashing for Undergraduates, and he explains in very simple terms why this works. So if you want to understand more, you can read this. It's a very easy to read text. But what underlines all this is this random graph idea. So this is the profound reason. Okay, so finally it's a simple scheme after all, right? It's a very simple and elegant scheme. So we have lookup and delete, which is worst case constant time, very easy to do, just two probes, and insertion, which is expected constant time. So this is the price. So the price is that insertion is no more constant time, it's expected constant time. So insertions that takes time. So deletions are supported, so it's no more static set as it was before. So here we don't assume that the set is static. We can have deletions, we can have insertions. What is important that we don't have too many elements at the same time. So what is important that we don't have elements that are, say, more than a half of the size of the table. So until we guarantee this, we can have insertions and deletions. So this is great because the previous constructions really assume that this set is static. So this is open addressing, no dynamic memory allocations, and so this is a very nice scheme. So the space usage is okay, but it's not great because we should have, because half of the buckets will be empty, at least half. And this is, of course, not very nice. But there is a very interesting generalization of this scheme, which actually supports a much better load factor. And this is very practical. So we can define a generalization in two ways. So first of all, we can have not two hash functions, but several hash functions, h hash functions, instead of two. So this is one generalization. And another generalization is that each bucket can hold actually not one item, but several items, B items. This is also possible, right? So if a bucket has several items, everything works. We just have to go through them and find the right object, right? And it turns out that when we allow more than two hash functions and more than one item per bucket, this improves greatly the load factor, really tremendously. So for example, in this paper, quite recent by the way, 2018, they showed that if we have 3 hash functions and 4 elements per bucket, then the load factor is almost 100%. This is completely amazing. So we basically use all the memory that we allocate. So this is a power of choice, because when we have flexibility, when we have choices, the memory usage is greatly improved. So this is really amazing, I think. So this is another illustration of the power of choice. So some tables that I found, I don't remember where, some maybe on internet or some paper. So they show the load factor, supported load factor, depending on the size of depending on the number of items held by one bucket. So if we hold only one bucket per one item per bucket, then it's 0.5. No, sorry. This is depending on the number of hash functions. So this first table is one bucket, one item per bucket, and different number of hash functions. So if you have two hash functions as in the basic version, this is 0.5, a little bit less even. If we have three hash functions, it's already 0.918. So it's a huge increase of the memory usage. Okay? It's really amazing that just using three hash functions instead of two, we have such a huge increase in the memory use. And here is another table which shows the dependence on the number of items held by one bucket. So here is two hash functions. And here again we see the similar phenomenon. So if we go from one item per bucket to two items per bucket, so the space usage increases from 0.5 to 0.9 almost.
And this theoretical number?
This I don't remember. This I don't remember. I don't remember if they were obtained experimentally or obtained theoretically. I don't remember. I think that the theoretical analysis becomes more complex because basically it means that instead of dealing with graph, we are dealing with hypergraphs. And for hypergraphs, the analysis is more complex. There are still things that are known about hypergraphs. But this number, I don't remember if they are obtained experimentally or theoretically.
Do you know real-life applications?
Yes. No, I think that Cuckoo Hashing is nowadays, maybe I have a slide about, yeah. So Cuckoo Hashing is very much practical. It's very much used in practice. And yes, it's, for example, I work in bioinformatics and I mostly am aware about bioinformatics application. I know that in bioinformatics people use this really in practice. So it's a very practical thing.
And what's the most popular hash?
Yes, I think this 3.4 is very good. So yeah.
So Cuckoo Hashing is more popular than other types of hashing?
I think so. Yes. Yeah. In practice nowadays, because a lot of work has been done recently. So it's pretty recent. So the invention is from 2001, I think. So it's relatively recent. So yes, now I think Cuckoo Hashing is really maybe something that is used.
Or soon will be used.
Yeah, already, yeah. So this is to illustrate precisely I put this slide. Well, this is, I don't know how convincing it is, but I just found this. I'm using. So this is because everybody is talking nowadays about machine learning and neural networks and deep learning and things like this. So there was a proposal from people from Google actually, who proposed also to use machine learning to replace data structures. So instead of having a data structure storing a certain set of keys, we will train a model that will tell us, that will give us, you know, the yes or no, that will replace the traditional classical data structures. And there was an answer to this that I found on the internet, who compared this neural network implementation with Cuckoo Hashing. So they actually advocate that Cuckoo Hashing is more performant than this. In my view, this is just to illustrate the popularity of Cuckoo Hashing, because comparing these Lond indexes and the classical indexes is a delicate issue because for long indexes we need training set, we need, it's two completely different approaches. It's, in my view, quite incomparable, but it's still interesting that they chose Cuckoo Hashing as a comparison. Okay, so this ends the hash table part of my lectures. So what we have? We have half an hour. Okay, so we have half an hour. I will continue and then we will see how far we'll go, and then we will see what we do tomorrow after that. Okay? So Bloom filters. So now we are done with hash tables. So now we are, so now my main point for the rest of my lectures is that hash functions actually have much more application than hash tables. So hash functions have numerous other applications than just hash tables. And one of the applications here, the first one that I want to consider, is so-called approximate membership data structures. So here we are talking about, so we are no more talking about hash tables. We don't store our keys anymore. We don't store our objects anymore. We want to comply with a different task. We want to build a data structure that will only tell us yes or no, the object belongs to the set or not. So we don't have the goal of retrieving the object. We don't have the goal of accessing the object. We just want to build an oracle that will tell us yes or no, the object is in the hash table or not. And this is actually can be done in following basically the same ideas as a hash table.
So for example, you want to remember whether a person is vaccinated or not?
For example, yes. Okay, good example. We will return. Let's return to it. So first, I will summarize what. So the data structure is called Bloom filter, and I will summarize what this data structure does. So it sort of generalizes the bitmap representation of sets. So the bitmap representation of sets that when we have as many bits as there are possible objects, so the size of the universe, and we put 1 if the object belongs to the set and 0 if not. So this follows basically the same idea. So we will store a bitmap, and the ones in this bitmap will tell us if the object belongs to the set or not. So the operation we will support will be insertion and lookup. Unfortunately, we will not be able to support deletions, at least in this basic version of the data structure. So we're only able to insert objects and look up for objects. And so lookup only checks if yes or no the object belongs to the set. So there is no really access to the object. There is no satellite data, so-called. And moreover, so the data structure will make mistakes sometimes. So the mistakes will be only one-sided. So if the object belongs to the set, then the answer will be always yes. If the object doesn't belong to the set, then the answer will be no, but sometimes it can be yes. So so-called false positives. So sometimes we may have some false positive with small controllable probability. So deletion is not supported, I already said, and so the whole point about Bloom filters that the data structure will be very space efficient because we don't store keys now. We only store information about keys. So the space will be not dependent on the space we need to store keys. It will be only dependent on the number of keys. Okay. So now returning to your example, if we store, yes, it's a good idea to store vaccinated people, for example, in a Bloom filter. So in this case, if you give me a person, I'll check against my Bloom filter and will tell if he or she is vaccinated or not. But the problem is that
assuming that only few people are vaccinated, because otherwise you can just store an array for every person.
Yes. This is a good point. Yes, the number of stored objects should be much smaller than the universe. But with this example, we have a slight problem with false positives because in some cases, for some non-vaccinated people, we will answer that they are vaccinated, which is maybe a not very desirable situation with this example. So in this case, we would maybe be better to store non-vaccinated people in our Bloom filter if their number is small. This would be a more desirable situation. Yes, unfortunately.
Less than 10% non-vaccinated.
Yes, unfortunately, yes. We have, in Russia at least, we have probably more non-vaccinated than vaccinated nowadays. So here I have another example, which is forbidden passwords. So, for example, if you implement some web service and you want to support users, how it's called, private space, or how it's called, accounts, you want to create a system of accounts, of passwords, and you want users to specify only complex passwords, and you have a list of simple passwords that you want to forbid. Then you can store them in a Bloom filter, and what will happen is that sometimes there will be false positives, but false positives means that user specified a good password, but the system says no, it's not a good password, specify another one. Well, it's not a big deal. It's not a problem. So Bloom filters are also useful and widely used, but I will talk later about this. Okay, so this is a summary. So now how it works, you probably already guessed, or you maybe already know, because I didn't make my.
Can you first say if we want to store n forbidden passwords?
Yes.
How much bits do we need?
How much space do we need? Yeah. I'll tell this on the next slide. So this will be next slide. So this is a formal definition. So we have D. Okay, we allocate a bitmap of say m bits. Okay, we have D hash functions. D to be defined later. And when we insert a key, we set corresponding bits to 1. So we set D corresponding bits to 1 unless they were already ones. In this case, they stay 1. And if not, they flip. Okay. And when we look up, we check if the corresponding bits are all ones. If they are all ones, we respond yes. And if at least one is 0, then we respond no. And that's how it works. So having several hash functions, you can probably figure this out, that is needed to decrease the the probability of false positives. So when we have several hash functions, so the probability to have several ones by chance becomes smaller, right? So this is the idea of having several hash functions. Did you understand the definition?
Yeah.
Okay. So this is the illustration, I think, from Wikipedia. So we have 3 hash functions here. So 3 objects inserted to the hash table. So all corresponding bits are 1s here. And if we query some other object W, so we go to the 3 locations corresponding to the hash functions, and one of them turns out to be 0, so we respond no. W is not. But if the third hash function would by chance point here, for example, then this would be a false positive. So we would respond yes, whereas the right response is no, right? Okay, I think you probably know this already. I mean, I think some of the students, I know that you told me that you saw this in class, so you know this. Okay, so
as far as I remember, this structure is not very fast, right? In practice.
So the speed is clear. So we need to when we query, we need to check D locations. So this is clear. So what is the value of D in practice? We can talk in a moment. It's some reasonable constant. But then you can also in real life applications there is also an issue of cache misses, because if you have a huge Bloom filter which takes I don't know maybe tens of megabytes or hundreds of megabytes or maybe even gigabytes, then there is a question of hash misses, but this is, let's not talk about this software engineering issues because it's a different. But so Bloom filters are known to be a bit problematic with respect to this cache misses problem, but otherwise. If everything is in the main if everything is in the main memory, then they are pretty fast. So there is no problem actually. So this is the analysis of Bloom filters, which is very clean and easy. If you are not tired, we go through it. So I propose that we go through this analysis. It's not complicated, okay? It's so what we want to compute. We want to compute the probability of false positive. So this is the main issue, right, with Bloom filters, depending on n, m, and the number of hash functions. Okay, so n is the number of objects, m is the number of bits, and d is the number of hash functions. Okay, so the analysis is pretty simple. So let's first compute the probability that some specific bit of the filter is 0. So it is 0 if it has not been touched, so to speak, by any hash function on any object, right? So the probability that the bit is, so for a given object and a given hash function, the probability that the bit is hit by this hash function is 1 over m. So the probability that it's 0 is 1 minus 1 over m. And since there are d hash function and n objects, so we raise all this to the power of nd. So we obtain this expression. This is the probability of, after inserting n objects, the bit is still 0. Some specific bit is still 0. And this is approximately this, right? Are you convinced?
I don't understand why you make it with exponential functions.
And
you can just say dn over m if you select a random.
No. We want to compute, because this is 1 minus, because we want to compute the probability that a bit is 0. It has not been...
Fixed bit, but you're interested in a random bit.
Yes, a fixed bit,
Yeah.
Random fixed, yes. Random fixed, I mean fixed bit.
Yeah, so you, key arrives.
Yes. No, I have already inserted n keys. Assume I have already inserted n keys.
Yeah. And now?
So the question I ask is, what is the probability that a fixed bit is still 0, has not been turned 1?
Yeah, I agree with calculation. Just think that.
So what troubles you in the calculation?
It can be done easier, I think. And
What,
so I
how
wonder
it
why
can
not
be easier? How it can be easier?
Because you're not interested in fixed bit, you're interested in random bit.
No, I'm interested in fixed bit. So, okay, what is the probability?
It's not, yeah, I understand.
No, fixed bit.
Yeah, it's clear. Fixed bit, you need this formula. But for random...
No, it's a fixed bit, yeah.
Yeah, I understand, but...
No, because we want to compute the probability of a false positive, which means that, which will be the probability that the bits are ones sort of by chance. I mean...
Yeah, but this D, random and independent bits,
yes.
will be checking.
Yes, but... yes, random and independent, but...
So you can just... Okay, it's a detail, it's not important. I just think you can write directly 1 minus dn divided by m. But it's somehow better.
No.
It's large. Okay, I see. Yeah.
No. We have to rise to the power because we multiply the probabilities.
Yeah. Okay, I understand that.
Yeah.
If you do it like this, it's better probability. Sorry.
Yeah. You mean by union? Okay. Okay. So let's denote this by p. This probability, and then the probability of false positives is that all the d bits. So false positive means that we are trying to look up, we are trying to query a key which is not in this set, and we by sort of misfortune we have all the bits once. So what is the probability of this event? So the probability is 1 minus p to the d, right? So 1 minus p, right? So we have this probability of false positive. So this is a false positive probability depending on n, m, e, d. And then what we can do is to find the optimal d. What does this mean? So this means that if d is too small, so intuitively the false positive probability will be high because we don't have enough bits to discriminate between objects which are in the set and which are not. Well, I am informal here, but so intuitively it should be clear that too few hash functions is not good, and too many hash function is also not good. Because if we have too many hash functions, then our table, our bitmap is too much populated with ones, and we have false positive for another reason, because there are too many ones in. Okay, so there should be some optimum. There should be some golden middle in this in D. Okay, and you can simply do it by simple calculus. So if you can compute the derivative on D and compute solve the equation and find the optimum D. Okay, so I skip this, but this is a routine. Calculus, routine analysis, and well, it's not. You have to spend maybe 10 or 15 minutes because the derivative here is not immediate, but this is mechanical, and And if you do this, then the optimum number of hash functions will be natural logarithm of 2 times m over n. So m over n is the number of bits per element. So it's sort of inverse to load that we had before. Okay? So m over n is the number of elements. So this comes to your question that you asked, how many elements. So m over n is the number of bits per element, right? So the number of hash functions is some constant like 0.7 times the number of bits per element. So I think I have just an illustration to this phenomenon that, well, for example, here m over n is 8, so we have 8 bits per element, so 1 byte per element. And in this case, the optimum number of hash functions is something like 5, 6. Okay? So, so if we substitute this optimum number of hash functions to the false positive probability formula, then we obtain the false positive probability, which is equal to this, some constant, 0.61, to the power of m over n. Okay, so you obtain a very clean and simple formula for the false positive probability. Very simple formula. And this is interesting. So if we have, like, for example, 10 bits per element, so this constant rise to the power of 10 will be already less than 1%. Okay? So by allocating 10 bits per element, which is independent, of course, on the size of the keys. So keys can be very big and very complex. But if you allocate 10 bits per key that you have, then the false positive probability is less than 1%. Okay? So now you can also turn this around and say it on the other way around. So you can ask the question, how many bits do we need to ensure a false positive probability epsilon? So you can solve the epsilon equals this. You can solve this on m. And you obtain then m equals binary logarithm of e times n times binary logarithm of 1 over epsilon. So which means that we need binary log of e times binary log of 1 over epsilon bits per element to ensure the false positive probability epsilon.
I'm going ahead. Do people know lower bounds for this formula?
This is my next slide. Great. So you are a real theoretician, so you immediately ask the right questions. Yes, it's a very good question. It's an excellent question. So okay, so did you get this? Can you? Okay, perfect. Okay, perfect. So now.
So maybe you should check the chat from time to time.
Yeah, I didn't check because actually. Yeah, there is nothing in the chat, but I know that Bloom filter is something that some people know because it's quite popular in programs of algorithm courses. So okay, so I was here. So now about the lower bound. Let's talk about the lower bound. It's a very good question, and maybe it will be my, because we should. Okay, so it's a very good question. So what is, how good is this? Let me now infer the lower bound. So the lower bound will be information theoretic lower bound. So we will compute how many different Bloom filters for sets of size n we may have we need to have at least the lower bound, and then we will take the binary logarithm, right? So this is information. I don't know, I maybe should ask students if they understand this reasoning. So if you don't know what is a deformation theoretical lower bound is, I just repeat what I just said. So when we want to represent objects from a set of some cardinality, so we need at least the number of bits, which is a binary logarithm of the cardinality, right? If we is this clear what I said, or?
What you said is clear, but what's on the
Yeah, but no, because you're going fast, so I want to make sure that everyone follows. So
for every set of n keys, you need a different Bloom filter. Is the idea, and so this Bloom filter is encoded in bits.
No, you go fast. So I want to explain that why we take the binary logarithm of the number. So this is the first idea. So this is called information theoretic lower bound, and this is in general lower bounds are difficult to obtain. So we don't have many tools for lower bounds, but the simplest and the most maybe straightforward way to obtain lower bound is to count the number of objects, possible objects that we need to represent, and take the binary logarithm. So okay, so now let's try to count the number of possible Bloom filters that we need to represent different sets of n objects. So each Bloom filter for a given set, so what it does, so we have a set of n objects. So we have a set of n objects for which the Bloom filters answers yes, but it also answers yes on some other object. So this is our universe, which is huge. Okay, so we have different sets of n objects, and for each set we construct a Bloom filter. Okay, so we want to estimate how many different Bloom filters. So so our Bloom filter answers yes for the objects of this set, and also answers yes for some other objects, right? These are false positives. Okay, and answers no for the other objects of the universe, right? So the size of these false positives is the cardinality of these false positives is epsilon u. I should write epsilon u minus n, but u is very huge with respect to n, so I neglect it. Okay. So and this specifies a Bloom filter. So the Bloom filter is specified actually by this set, by this surrounding set, right? So a Bloom filter is specified by this set because the Bloom filter answers yes for the questions, answers yes for the objects of this big set, let's say, and no for the other objects. So Bloom filter is specified by this big set, right? Right? So what we need to count is the number of big sets covering all possible small sets. Okay? So we want to count the number of these sets, big sets, let's call them big sets, covering all possible sets of size n. So this is a combinatorial problem, actually, which is not simple. So there is some Erdos type, questions that so the exact number of such sets, it's a complicated combinatorial question. But there is an easy lower bound. And the lower bound is obtained by simply dividing the number of possible n sets, which is u choose n, by the number of small sets covered by each big set. So the lower bound is obtained in the assumption that small sets covered by different big sets are disjoint, which is not true, of course, because there can be different big sets covering the same small set. But since we are interested in the lower bound, we can, for the purpose of the lower bound, we can say that let's assume that these sets are disjoint. So this can only increase the how to say, this can only so the number that we obtain can be only smaller than the real number. Okay, so we will obtain a lower bound, which will not be a true lower bound, but so by this division we obtain a lower bound. Okay, and this is now so this is approximately this. So why? Because if I approximate, so I approximate I don't know, n choose m by n over m to the power of m. If I use this approximation, then this will be u over n to the power of n divided by epsilon u over n to the power of n, and this is 1 over epsilon to the power of n. So by taking the binary logarithm, we obtain n times log 1 over epsilon. So the lower bound says, this lower bound says that we need at least log 1 over epsilon bits per element. And the Bloom filter takes a little bit more. Yeah, pretty close, yes, it does pretty well. So it's only a small constant factor away from the lower bound. So this is a
more clever analysis of lower bound exists to make it bigger. I don't know.
No, it's rather the other way around. There are schemes which approach this lower bound.
Okay.
Yeah. So I will continue because time. So well, time is it now? Oops. Yeah, we should conclude. So I will conclude with Bloom filters. So Bloom filters are very simple. Well, one obvious advantage of Bloom filters is that this is a very simple data structure and very easy to implement. So to implement, it's like a few lines of code. So so some good properties. So in a good Bloom filter, in a well-dimensioned Bloom filter, we will have about half of the bits should be 1 and half of the bits should be 0. This is immediate consequence of the formula of the probability of 1. So another nice application is that if we have two Bloom filters for two sets of the same size and with the same hash functions, then we can obtain a Bloom filter of the union by ORing these two Bloom filters. For intersection, unfortunately, it doesn't work so well because this is usually the question that I ask my students, if this works for the intersection, but since we don't have time, I will tell the answer. And since the students are far, So for the intersection, it doesn't work by ending the Bloom filter, because we may have after ending we may have a once in our Bloom filter which should not be there. So so we may have situations like this that I will finish in 5 minutes. So we may have so Bloom filter for one set where we have some object X with one here and one here. In the another Bloom filter, we may have some object Y, which has one here and maybe one at the same location here. And when we take the end, so assume that Y doesn't belong to S1 and X doesn't belong to S2. So when we take the end, this one will stay in the end, and this one should not be in the intersection. So this doesn't work with intersection. And another observation is that if a Bloom filter is sparse, means that if it has too few ones, then we can actually halve its size by redefining hash functions. So what we can do is we can take the OR of the two halves and redefine the hash function accordingly, and we don't need to compute the Bloom filter from scratch again. And it has endless applications, so it's a very practical data structure used everywhere. So this I found on, don't ask me how it's used in Google Chrome, for example, I don't know. But I know that it's widely used in applications, so it's a very, very practical thing. Okay. So that's it for today. So the next, tomorrow I think, well, so tomorrow the question is if so it's currently there is only one lecture planned, but the question is if I do one lecture or two lectures as today. So I think I will maybe do more than one lecture, so I can do 2 lectures if you are okay with that. So I will continue with a little bit with this hash-based data structures, and then I can do a lecture about locality sensitive hashing. That's another type of hashing. So are you interested?
Yes,
so I will have at least one listener tomorrow. Okay, then let's do this. So that's all for today, and see you tomorrow then.
Okay, thanks.
Okay, thank you.